talking about the geometry of Debarre-Voisin varieties. Thanks. Please take it away.
Okay, thanks. So first of all, I'd like to thank the organizers for organizing this wonderful event and for giving me this opportunity to talk. So I'm going to talk about the geometry of the Debarre-Voisin varieties. This is a joint work with Vladimiro Benedetti. So it's a bit embarrassing because I was going to talk about the proof of the integral Hodge conjecture for cubic fourfolds as a motivation example, but we just saw this morning. But I'm going to repeat it anyway, so hopefully I can provide some more details. So let's consider a cubic fourfold inside P5. So this is a cubic hypersurface given by a cubic polynomial. And this is a Fano variety, so it's rationally connected and so it's covered by lines. And we can consider the F here. This is a Fano variety of lines. So this is a subvariety inside the Grassmannian 2,6 that parameterizes lines contained in the cubic. So for example, if I take a point here, this corresponds to a line in the cubic. And this is a very famous theorem by Bobby-Donaghy that we just saw this morning. The variety of lines is hyperkähler of a K32 type. So this means that this is a compact Kähler variety that has simply connected and has an nowhere degenerated symplectic 2 form, and also is deformation equivalent to the Hilbert square of a K3 surface. Now, if we look at the Hodge structure of these two varieties, so here I show the Hodge diamonds of this two four-dimensional variety. So on the left, we already saw this. So for a cubic fourfold, it's almost trivial, except in the H4, where we have this rather big Hodge cohomology of type 1, 21, and 1. So this is a middle cohomology. So there's I can use the cup product. This gives it a structure of a unimodular lattice. And there's a class here. This is the complete intersection of two hyperplane sections, and this is always algebraic. So I will take the orthogonal complement of this class. This is what is usually called the vanishing cohomology. And since the whole H4 is of type 1, 21, and 1, so this part here will have 1, 20, and 1. Now on the right-hand side, we have a hyperkähler fourfold. So by the general theory of hyperkähler varieties, the H2 is equipped with the Boville-Bogomolov-Fujiki quadratic form. And if we look at the whole lattice, this is not a unimodular lattice. So this is in fact different from the H4 that we have on the left. This is a lattice of discriminant 2. And inside we have the class here, the H. This is a class of polarization. So since F is defined inside the Grassmannian 2,6, there's a Pluke embedding. So this is a polarization class. And its orthogonal complement is the primitive H2. And so here we also have one piece that is of type 1, 20, and 1. So what we are going to do is we compare the two parts here, the vanishing part of the cubic and the primitive part of the Fano variety of lines. So now we like to compare these two Hodge structures. And to do this, we use the point line correspondence that we already saw this morning. So I consider the set of pairs of point and lines, such that the point is containing the line and containing the cubic. This admits naturally two projections to the cubic fourfold and the Fano variety of lines. So for example, here you have to imagine that this is a product of the cubic and its Fano. And if I take a line here, this is projected onto a point inside the Fano variety of lines. And in the other way, it's projected onto a line in the cubic. Now this is the so I should mention that this map here, the projection to the Fano variety of lines, this is a P1 bundle. Since the fibers, they are all naturally just lines. This is the second part of Bobby-Donaghy theorem. It says that if we we start from H4 on the cubic, and we pull it back to the incidence variety I. Then we push forward to F. Then this goes from H4 of the cubic to the H2 of the funnel, and this gives an Hodge isometry when we look at the vanishing part and the primitive part, because otherwise the lattice, they don't have the same discriminant. And here the negative ones, this means that there's a change of sign, but the lattice, they are mostly the same. And the proof of this is they use the description of the things. This map here is the P1 bundle. So the cohomology ring of a P1 bundle is behaves very well, so we can compute everything explicitly, and we can show that this is the Hodge isometry. And now the interesting corollary is that we can use this to deduce the integral Hodge conjecture on X. So this is a theorem that we saw this morning for since the final variety of lines is hyperkähler of K3 type. So all the one-dimensional Hodge classes on it are algebraic. So we use this correspondence. Now this time we go from F and we first pull it back to I, then push forward to X. So we go in the other way, and then we map the H6 of the final variety of F to the H4 of the cubic fourfold. Now the above theorem by Bovie-Donaghy, this shows that this actually the image generates the entire H4, so all the Hodge class will be algebraic. So here I write this like this. In fact, we saw that this part already generates the entire H4, but I like to keep this part here since it's always algebraic, and we are going to see some analog results in the Debarre-Voisin case. Maybe here I also give a geometric interpretation for this. So if we keep this same image as before, so what we do is we take we take a curve on a final variety, and we pull it back, and we get a one-dimensional family of lines. So this form a surface, and then we push it forward. So this gives a surface inside the cubic. So this means that all surface classes in the cubic fourfold, they are generated either by the complete intersections, which is all the surfaces of this type. So now I'm going to talk about Debarre-Voisin varieties. So for this, instead of considering a cubic polynomial, we start from an element of this type. Sorry. So this is a 3 form on a 10-dimensional vector space. And I can associate 3 different varieties to this element sigma. So I denote them by x1, x3, and x6 because they live inside the Grassmannian 110, 310, and 610. So I'll first talk about the second one here. So this is simply just a hyperplane section of the Grassmannian 310, and it's a 20-dimensional hypersurface final variety. And this is what we saw in Emmanuel's talk. So this is a third example apart from the cubic fourfold and the Gaussian Mukai, where we have an example of a K3 category. So it's this case here. And for the X6 here, we can define similarly. We consider the set of 6-dimensional vector spaces where the 3 form sigma vanishes. So this can be realized as zero locus of a section of a 20-dimensional vector space on the Grassmannian 610. So this gives a variety of expected dimension 4. And finally, I explained the construction of this variety X1 here. This is a bit more complicated. So if I take the projective space V9, so each element is just a one-dimensional subspace V1, and I contract it with the 3 form, then I get a school symmetric 2 form on V10. So now the one-dimensional vector space V1 is always going to be in the kernel of this form. So it cannot have rank 10, which means that generically it will have a rank 8. And I demand X1 to be the locus where this rank drops even further. So this is the locus where the rank of this 2 form is less or equal than 6. So this is certain degeneracy locus in the P9. And this was first studied by Beskin, and this is a final variety of expect dimension 6. So now this is a theorem by Debarre-Voisin. They showed that the third variety here, the X6, this is the hyperkähler of K3-2 type. So in our situation, we have two varieties, two final varieties of dimension 6 and 20, and we have a hyperkähler of dimension 4. This is somehow similar to the situation of a cubic fourfold, except that we have two final varieties that can be seen as a counterpart of the cubic fourfold. So now I'd like to show their Hodge diamond. So first for the hyperkähler one, since this is of K3 type, is Hodge diamond is going to be exactly the same as the variety of lines, which means that in H2 there's going to be a piece of 1, 21, and 1. And the rest is just the same, and it's not of particular interest in our case. And now for X3 and X1. So X3, since this is a 20-dimensional variety, it has a lot of numbers here. But essentially by Lefschetz hyperplane section, this is a hyperplane section of the Grassmannian 310. So all these classes here, before the middle cohomology, all these classes here, they are actually generated by pullbacks of classes on the ambient Grassmannian, which means they are pullback of Schubert classes. And on the middle cohomology, we have a Hodge structure of type 131. So in fact, there are 10 of them that are still come from the pullback of Schubert classes. And also, since this is a middle cohomology, this is a unimodular lattice equipped with the curve product. So here we have 10 Schubert classes plus this part here, the vanishing part that is also, again of type 120 and 1. And we have this part that is going to be of interest to us. Now on the right-hand side for this 6-dimensional X1, in fact, we have 3 copies of a Hodge structure that has this shape 1 something 1 on the H4, H6, and H8. So I will be I'll be looking at the H6. So since this is a middle cohomology, this is a unimodular lattice. And if you look at this number here, this is 22. So, and what we want is 20. So in fact, I claim that there are 2 classes that are always algebraic. So first there's the H cube. So this is a complete intersection of 3 hyperplane sections. And there's another class pi that I'm going to come back to in a moment. So I claim that there are always 2 classes that are algebraic. And if I look at the orthogonal complement of these 2 classes, I get the vanishing part. So this is again a Hodge structure of type 1, 20, and 1. And now the goal is to compare these 3 Hodge structures of the same type. So again, we will use the same idea that we studied this using the incidence correspondence. So here I use the same picture as before, but the situation is going to be a bit more complicated. So here is first I consider the incidence correspondence between X3 and X6. So this is a variety X3, and this is the hyperkähler X6. So a point here, this corresponds to a 6-dimensional vector space. And if I look at the fiber, this is going to be all the 3-dimensional vector spaces contained in V6. So this fiber here, this is a Grassmannian 3V6. So you have to mentally replace this line with the Grassmannian 3,6, and it projects onto a Grassmannian 3,6 contained in the hyperplane section. So we have a very similar picture, except that in this case, actually this incidence variety does not dominate X3. So if we compute the dimension, this only covers a sub-variety of X3. Now, if you look at the second case, so here if I pretend that this variety here is X1, this is X6, and again I take a point here, this is the 6-dimensional vector space. So the fiber here, this should be the set of V1 contained in V6, so it should be a 5-dimensional vector space. But this 5-dimensional vector space is not contained in X1, so I have to intersect it with X1, and I get a 3-dimensional subvariety. So And I always get a three-dimensional subvariety, and it always has the same shape. This is what we call a Palatini threefold. So this means that all the if I move v6 in x6, and all the fibers they are this Palatini threefold. So in particular, this pi here. I mean, if I push forward the fiber here into x1, I get a three-dimensional subvariety containing x1, and its class is what I denoted by pi here. So this is a class in the middle cohomology. Now this is what we obtained with Vladimiro Benedetti. So we use this correspondence to show the exact same to show the analog of the result in the Bovie-Donaghy. So if we look at the first correspondence here, so we go from the middle cohomology of X3, we pull it back to the incidence variety, and then we push it forward. Then this gives an Hodge isometry between the vanishing part of the H20 of X3 and the primitive part of the H2 of the hyperkähler. And for the six-dimensional X1, this is a bit slightly different here. I need to first apply Lefschetz. So I go from H6, then I go to H8, then I use this pull back, push forward. Then I can arrive in the in the H2 of the hyperkähler, and this gives the Hodge isometry. And also all the three Hodge structure that we see here, so they are actually related by Lefschetz operators, and we can show that if we restrict to the vanishing part and using the Lefschetz operator, they are actually isomorphic as abelian groups. Now, one corollary of this is that we can use the same idea as in the case of cubic fourfold to show the integral Hodge conjecture for x1 and x3. So the proof is essentially the same, that we go from in the other direction, that we go from the x6, the one cycles on x6, and we put it back and then push it forward onto the other direction. So in particular, in the case of x3, you can show that the H20 is generated by the 10 Schubert classes, which are always algebraic, and the other part is the pullback and push forward of the one cycles on the hyperkähler. These two summands generate the H20. So since this here is algebraic and this here, they are just one-dimensional family of Grassmannian 3/6. So they are also algebraic, and this generate all the classes of type H1010. And for X1, similarly, we can do this thing, and so we have one part that is always algebraic, that is generated by the class of a complete intersection and the Palatini threefold, and the other part is coming from the hyperkähler. One cycles on hyperkähler, so these two they generate the H6, and so we can show that the all Hodge classes on H6 they are algebraic. Now, this is actually the most difficult part. Once we know the integral Hodge conjecture holds on the middle cohomology, for the other, they are just basically they are just Lefschetz. Maybe just here I note that in the case of X3, there's a slight difference. So we see here in this huge diamond here. So here we show that everything is algebraic. And here, all these classes they are Schubert classes, and using Poincare duality, we can somehow show that the classes below the middle cohomology they are also pullbacks of Schubert classes. The problem is that in fact they only generate an index 3 subgroup, and there's an extra algebraic class. So this is provided by the class of Grassmannian 3/6, so which is a fiber of the incidence variety over the hyperkähler. This is quite interesting, since this is an extra class provided by this picture. And for X1, we need some extra argument to show that this also holds on the other cohomology group. But the main idea is we use the same construction as in the case of the cubic fourfold. And so also one corollary is that now we show that the integral Hodge conjecture holds for x3. So since the integral Hodge conjecture respects the semi-orthogonal decomposition, this means that the non-commutative integral Hodge conjecture also holds for the K3 category that we defined, that Emmanuel defined in his lectures. And there's a remark that there's a similar work done by Bernardare, Fadigendi, and Manuel. They also related the Hall structures of x1 and x3, but they use a different method. They passed from x1 to x3 via a different variety, which in my notation would be called x2. So this is defined inside Grassmann in 210. So in particular, we have this diagram here. So every like they all share the same Hall structure, and it's a very nice picture. And but what we did is we passed this through the hyperkähler X6. So in this way we were able to use the integral Hodge conjecture on one cycles on hyperkählers and prove the integral Hodge conjecture for X1 and X3. So now I'd like to briefly give an idea of the proof of the theorem of here on the Hodge isometries. So basic idea is that the first, this is a topological invariant. So which means that if we have a family of we have a family of this kind of varieties, if we can show this on one element, then this will deform over the entire moduli space. And so maybe this is not very important. So I jump to the second part here. So we know that once we know that this is an isomorphism of rational Hodge structures, it will suffice to show that the two quadratic forms, they are actually coincide. So we only need to determine this. There's a coefficient that we need to determine. And to do this, we go in the other direction. We specialize to special members where there are extra algebraic classes. So we can do some explicit computation and verify that the scalar is -1, which is what we want. So to do this, we studied some devices in the moduli space of Debarre-Voisin varieties. So these are the locus where there are extra algebraic classes, so we can study them. For this moduli space, there are actually 3 different models for the moduli space. So on the left-hand side, we have a moduli space for the 3-form sigma. So this can be realized as a GIT quotient. Like we take the space of all 3 forms and we quotient by the action of the SLV10. And in the middle, we have a coarse moduli space for polarized hyperkähler varieties. And on the right-hand side, we have the period domain that we already saw in earlier talks. So this basically, this is a space that parameterizes Hodge structures on the H2 of the hyperkähler. Now there's this picture here that, so first we have a map from M to the moduli space of hyperkähler. So this is the map, this is the map that maps 3-form sigma to the X6 it's associated. So this is a construction by Debarre-Voisin, and this is shown by O'Grady that this is this is birational. The 2 spaces are birational. And here we have a period map that maps hyperkähler to its period to the Hodge structure on its H2. And this is by global Torrey theorem. This is an open embedding. So basically, we have 3 spaces that are all birational. Now on the inside the period domain, the space here, there are some naturally defined devices they called Higner devices. So this is we constructed it using the lattice structure on H2. So we can just take some element inside the lattice, and this gives us some hyperplane inside the projected space. And when we do the quotient, this gives some devices in the period domain. And in the case of K32, these Higner devices, they are characterized by a number called the discriminant. So they can be numerized using this 2D here, and it's always an even integer. On the other hand, in the GIT quotient M on the left-hand side, the devices here, they come from SLV10 invariant hypersurfaces on the projective space here. So this kind of information allows us to describe the geometry of this, of the geometry. So this is our result. Is that we consider the 3 devices in the GIT quotient coming from SLV10 invariant hypersurfaces. So here I denote them by these 3310, 1610, and 477, due to the obvious reason that there exists some subspaces over which we have a certain degeneracy. For example, here the 3310 means that there's a V3 containing V10 such that sigma vanishes on V3, V3, and V10. And this is clearly an SL-V10 invariant condition. Now, if we consider and by parameter count, we can show that these are actual devices. They are devices in the moduli space. So now, under the period map, these 3 devices they are mapped to Higner devices in the period domain D20, D24, and D28. This is a discriminant of the corresponding Higner devices. And what's more interesting is that since we have this description here, we can use this description to study the geometry of the 3 varieties in these situations. So precisely in the 3rd case, D477. So for example, in this case, we have a distinguished flag V4 containing V7 containing V10. And we consider all the V6 that is between the 2. So we consider 6-dimensional subspaces that contains V4 and contained in V7. And this gives a projective 2 plane. And this is going to be contained in the hyperkähler X6. So this gives a Lagrangian plane. And now in fact, the inverse holds too. That means that any Lagrangian plane inside of such X6 will always be of this type. Now, this particular case allowed us to conclude the proof of the Hoja isometry, since we have this extra algebraic classes, so we use them to compute the coefficient in the quadratic forms, and we verify that it's -1. So this allows us to conclude the proof. And for the other 2 devices, there are also some geometry, but I don't think I'll have time to explain. What's perhaps what's interesting is that in these 2 cases, there are some K3 that appear. For example, in this case, there's a K3 surface of degree 22 that appears, and the hyperkähler is actually singular along this K3 surface. And in the 2nd case here, the hyperkähler X6, it contains a uniruled divisor D, and this divisor is uniruled over a K3 surface of degree 6. And this conic fibration, this gives a Brouwer twist on the K3 surface. So in this case, we get the twisted K3 surface, and it would be interesting if we can somehow show that the K3 category in this case would be equivalent to the derived category of this K3 surface. So that would be well, for now, I think nobody has any idea how to do that, since the K3 category is quite complicated in this case. So that's the end. Thanks.